And here is the problem that represents those visuals. The year is 2056. A high Earth orbit relay information satellite that is non-geosynchronous, meaning that it does not have a period of 24 hours, used to communicate with the moon base, has a mass of 3,600 kilograms. It is orbiting in a perfect circle around the Earth at an altitude of 125,000 kilometers. How long does the satellite take to make one complete trip around the Earth? Alright, so for like any problem, we have written down our knowns. So we have the mass of the satellite, mass of the Earth, the radius of the Earth, the altitude that the satellite is above the Earth, and our gravitational constant. Now, first we have to find our value for our force of gravity equation and also our centripetal force equation. So the R value is going to be equal to the radius of the Earth plus the altitude, and that is going to be equal to 1.31371 times 10 to the 8 meters. And like it says in the question, it is asking us for us to solve how long does the satellite take to make one complete trip around the Earth, and this is also known as the period. So period is what we are solving for. Now, before we talk about anything else, let's talk about the eccentricity of this satellite. Now, the eccentricity is going to be equal to the distance between the focus points divided by the length of the longest axis. However, in this question, it states that we are orbiting in a perfect circle. This means that the distance between the two focus points is going to be equal to 0, and 0 divided by anything is going to be equal to 0. Therefore, our eccentricity is 0. Now, if we want to solve for the period, we first have to solve for the velocity of the satellite. And because, again, we are orbiting in a perfect circle, we can say that our force due to gravity is going to be equal to the centripetal force. This also means that our velocity is going to be constant throughout our entire orbit. Now we can break this equation down into a more complex equation, and it's going to be gravitational constant times the mass of the satellite times the mass of the Earth divided by the r squared. It's going to be equal to mass of the satellite times velocity squared divided by the r value. Now, because we're solving for velocity, let's now rearrange for velocity. So multiply by r, the square, and I see we have 2 mass of the satellite, so we get rid of that. And then let's get rid of the square by taking the square root, and we are left with velocity. It's going to be equal to gravitational constant times the mass of the Earth divided by r, and we're going to take the square root of that, and that is going to be equal to 6.674 times 10 to the negative 11 meters cubed, kilograms to the negative 1, seconds to the negative 2, multiplied by 5.972 times 10 to the 24 kilograms. And this is going to be divided by 1.31371 times 10 to the 8 meters, which is our R value. And we're going to take the square root of that. And to make sure we have our units right, we're going to have meters cancel with one of the meters here. So we're left with meter squared, and kilograms is going to cancel with kilograms to the negative 1. And right now we have meters squared per second squared, and we take the square root of that, we're going to be left with meters per second. So we have that all right, and our velocity is going to be equal to 1,742 meters per second. And let's remember that is a constant throughout the entire problem. So now we have our velocity. Let's solve for the circumference of this circular orbit. So we have circumference is going to be equal to 2 pi r, which is equal to 2 pi multiplied by 1.31371 times 10 to the 8 meters. And this is going to give us a circumference of 8.25428 times 10 to the 8 meters. Now we have the circumference and velocity. We can now solve for the period. So the period is going to be equal to circumference divided by velocity in this case. So that is going to be equal to 8.25428 times 10 to the 8 meters. This is going to be divided by 1,742 meters per second. Meters reduce meters. Our period is going to be equal to 4.739 times 10 to the 5 seconds. Or if we divide that number by 3,600, which is the amount of seconds there are in an hour, we can get 131.6 hours, which is just more recognizable, and we can actually quantify that in our brains. That is how you solve this question.